Well, guys, thanks all for joining us today. Welcome back to another event with Calyptus. We are Web3's career community for senior builders. And if you haven't signed up already, Ankit or Cal, if you wouldn't mind putting registration to Calyptus in the chat, please register with us. Make sure to check out our platform for learning more events like this or just job opportunities in Web3. But yeah, we're super honored to have Andres Monty with us today. Andres has spent the past 5 years working as a blockchain engineer, building for leading infrastructure startups like Climatics, through to being a smart contract auditor at our favorite audit firm, Oak Security. And now today he is co-founder and CEO at Scanworks, which offers security tools and infrastructure for the IBC ecosystem and beyond. And he's here today to run a session on all things bridge security in the Cosmos ecosystem. Yeah, can't wait to get going. Andres, I think before we just jump in, if you have any questions, guys, chuck them in the chat, and then myself or Callum will choose an appropriate time to kindly interrupt Andres the presentation. And that's it. Let's get going. Over to you, Andres.
Sounds good. Thank you for the intro, Dan. So yeah, hi everybody. I'm Andres Monty. And today we're going to talk, as Dan mentioned, about bridges, security, and everything between. So we are going to cover a bit like the different types of bridges and the road to IBC. So some words about me, even though Dan did already like a nice intro. So I'm co-founder of Range and Scanworks, been working in this space for a bit more than 4 years now. And yeah, like I've specialized in security, and specifically in security in the Cosmos ecosystem. So yeah, before starting at Scanworks, I was lead security auditor at Oak Security, as Dan mentioned. And yeah, I've also been like a bug bounty hunter, white hat, have built protocols, been core contributor, and a bunch of things. And now our key focus is Range. So at TLDR of Range is a security platform for blockchains and rollups, and our early focus is in the Cosmos ecosystem, and specifically bridge security and IBC. So I like to start the talk with a question for you guys, and you can use like the chat if you prefer, or speak up, whatever you prefer. But like the question is, how much, without Googling or using ChatGPT, how much do you think was lost due to bridge hacks in 2022? And I'll give 15 seconds for this. So hit the chat and just kind of say like what do you think as a best effort estimate.
Gone big. I like your style, Sibi.
Yeah, I mean, I'm seeing like a pretty good approximations. So like the real number, like it's hard to really quantify it, but like what we know for sure, it was more than $2.5 billion in 1 year. And like it's very hard, with such big amounts of money. At least for me, it's super hard to reason about them, right? Like, because they just look like very big numbers, but like they're very hard to reason about that. So I always like to make analogies with the real world, and more than $2.5 billion translates to, for example, 10% of the defense annual budget of Canada, very large country, which if you think about it is crazy, right? And I mean, I'm originally from Spain, and the amount that was hacked just in bridges in 2022 would account for more than 25% of our annual defense budget. So this is just kind of like to give you a sense of the highest stakes game we are playing here. I also bring like the defense budget of nation states, because in the other end, in the end of hackers that have performed these hacks are actually groups that supposedly are supported as well by nation states. So the stakes are definitely very high. So I guess that the key question, right? Like if it's, if bridges get hacked so bad, like why do we even need them, right? So there is one reality and one hard truth is that crypto today is multi-chain. You like it or not. So it started with Bitcoin, then came Ethereum with the vision of the world computer. The reality is that over the last 5 years, we've seen more and more different blockchains being deployed. You just have to go to CoinGecko and see like the vast amount of projects, and a lot of them are their own L1s and L2s. So yeah, crypto is multi-chain, and this is something that is not going to change. So it's a reality that we need to, handle with. Given that the crypto is multi-chain, users are going to want to transfer assets between different blockchains, and not just even transfer assets. They want to do swaps between assets in different blockchains. They might want to transfer NFTs and do a bunch of things. But the problem is that blockchains cannot really communicate with the outer world. And this is a property, very well-known property of blockchains. And that's why we've always needed oracles to kind of get information from the real world. Like, for example, what's the price of the pound or the price of the dollar? So we use oracles for that. And what are really bridges? So bridges are a very specific type of oracle, right? And I always like to use this analogy to reason about blockchains and bridges. So if we think as blockchains are isolated countries or isolated islands, and these are countries that they have their own traditions, they have their own rule of law, they have their own language, right? And then you have maybe another island, Island B, which has their own rule of law and their own traditions and also their own language. So like they really don't understand each other. And bridges are really sort of like the vessels in between, and are systems that understand both islands, both languages. And normally, like in crypto terms, like these traditions, languages, and things that I'm using, we normally call them protocols, right? So bridges are systems that sit in between and understand both protocols and let blockchains communicate with one another. I guess like a more formal definition, and the one that we are going to be using in this talk, is that a bridge is a system that enables us to transfer assets or send arbitrary messages between two different blockchains. So now let's circle back and understand how bridges really work. So there are normally three main components with bridges: the custodians, the debt issuers, which sometimes is the same, and then the relayers. And the relayers, we sometimes call them relayers, communicators, agents, oracles, whatever. So I think like to understand how a bridge works, the best is to go through like the user story, right? And let's say that in the very left, we have Alice, which is in Ethereum, has ETH and wants to transfer this ETH to another chain, whatever chain. So normally how a bridge works is that Alice would lock her ETH into a custodian. And when we talk about custodian, they are normally implemented as smart contracts, right? Like they can have different shapes, but they're normally implemented as smart contracts. So when Alice locks this ETH, then we have in the middle this agent relayer that is monitoring for certain events and watching the custodian. And when they see an event which is, hey, Alice locked their ETH, then they are able to transmit this information to the other chain, send a transaction to the other custodian or the debt issuer and say, hey, I can prove you that Alice locked this ETH, so let's mint a synthetic version of ETH that then she can use in the other chain. So we mint her AC ETH. That's how like the workflow works. If Alice wanted to say, hey, I did everything I wanted to do in another chain, I want my Ether back in ETH, sorry, in Ethereum, then what she would do is burn this AC ETH, and then the communicator or the relayer is going to be monitoring as well the debt issuer and the custodian, see, hey, Alice did burn this synthetic version of ETH, and then sends a transaction back to Ethereum, telling the custodian, now you can unlock the original ETH from Alice. This is a workflow which is multi-step, but very important. And here what we are trying to avoid is that Alice double spends her ETH. And double spending is one of the key challenges or features of blockchains, and is that the property that you cannot spend twice your coins, right? So in this case, like what we are trying to avoid is that Alice is able to lock her ETH, mint another version of it in another chain, and then unlock it in Ethereum. So would have double the ETH, half and half in each two chain. This would be, I guess, pretty good for Alice, but not that good for the rest of us. So this is really like the basic design or the basic mode that bridges are designed. Then now that we understand a bit better like how bridges work at a high level, we can try to organize them a bit. Like right now there are countless bridge projects and bridge protocols. So like to really understand them, it's good to organize them a bit. And normally we use two taxonomies for this. First is by design. So this is basically looking at who does the custody in each chain, how is this custodian really implemented, and who is the relayer, who can be the relayer, how is this verification and communication done, right? So like these are all design properties and design paths that different bridge protocols can take. And then the other way of organizing these bridges is by functionality. So basically this is looking at what assets can be transferred and what type of message can be sent. To reason about the different types of bridge designs, I think like this visualization is very good from Live-File Aggregator, and this is looking at the trust spectrum in bridges. So in the very left, we have what we call external validators-based bridges. These are bridges that the roles of custodian, the roles of relayers are made by external parties. So at the very left, we have the most centralized version of that, which is basically a multi-sig. And like a multi-sig of players can be like a foundation, can be like reputed players in the ecosystem, put in their reputation, and we as users are trusting that they are going to behave well, right? So this is a very centralized type of design. As we move more to the right, in the middle, we have bonded systems and insured systems. So here we are trusting to validators in another blockchain that they are going to behave well. In this case, there are economic incentives at play. So if they don't behave well, like they are going to be slashed, and there is more like economic alignment and incentives. And an example of this is, for example, Acceler. And then we have at the very right, like the more trustless version, which is CK bridges and light clients and relays. These are bridges that inherit the security of the source and the target chain. We are going to discuss later on what this really means. And now, like, let's also organize bridges by functionality. So, like, the first original type of bridges are what we call asset specific. So these are bridges that just look at bridging a specific asset. So, for example, Wrap Bitcoin, which is a bridge that connects the Bitcoin network with the Ethereum network and enable us to have a synthetic version of Bitcoin in the Ethereum network, just focusing on the Bitcoin as an asset. Then we have, as a second type, chain-specific bridges. So these are bridges that only connect one-to-one two different blockchains. So, for example, the Polygon POS bridge connects the Ethereum chain with the Polygon chain, and only assets flowing from these two blockchains. Then we have in the third type application-specific bridges. So these are bridges that focus only on a specific application. So, for example, AnySwap is focusing on swaps between between multiple different bridges. And then as a fourth category, we have what we call generalized bridges or arbitrary message passing protocols. And these are bridges that can literally send any type of message between these two blockchains, messages that are part of their protocol. So it's not just send a token, but you could even call a function in a different blockchain. And we have like a multiple examples for this. So now that we understand a bit how bridges work, and we kind of have a mental model to organize the type of bridges, and let's talk a bit about breach security. And this is not fine, really. Like it's pretty crazy, like the numbers that have been hacked like in recent years because of breach security. We already discussed like the analogies with the different national states, defense budgets, but even beyond that, like this is also like a existential key risk for the survival of our industry, right? Because in crypto we need more users. We always talk about mainstream adoption, but the reality is that if users get affected by a hack like this, like they are not coming back, right? And we've seen very relevant breaches that have affected many people of new users, that all the work that you did to onboard this cohort, this is very hard to get them trust back, right? So this is really like a problem for us as an industry. I'm a bit biased, but I think it's one of the most important ones that we should solve if we really want this technology to be used by the mainstream, right? So now we can think and try to understand, why this get hacked, or why do bridges get hacked more than other protocols? And then there are three key reasons here. The first one is that bridges handle a lot of TVL. So TVL stands for total value locked. And if we come back at the design of how bridges are designed, remember the custodian part, right? So normally you have to lock ETH or whatever asset it is to mint it in the other chain. The problem here is that you're locking this for a long time, and imagine that there are $10 billion of ETH minted in Ethereum, in Solana. Then what this means is the custodian in the Ethereum network is handling $10 billion. So if there is a bug, if there is a vulnerability and it gets exploited in all the process, like we could have, like hacks in the order of billions of dollars or hundreds of millions of dollars. So this is kind of like a very good honeypot for attackers, just because of the sheer amount of funds that these systems handle. Then, the hard reality is that some designs are better than others, and some teams have, either go for simpler designs or taken shortcuts just to be first to market. And, we've seen hacks happen to, centralized and multi-sig based systems that could definitely be avoided. Like sometimes hacks that are the software level are hard to be avoided, but, we as an industry have to put ourselves in a higher standard and just not use flaw bridge designs, right? And the third, and probably the most important, is that bridges are very complex, right? Like sometimes even more complex as a piece of software that the blockchains that they are integrating. Imagine that you're a bridge and you're connecting 5 different blockchains. You need to understand and you need to integrate like these 5 different blockchains. You might need to even implement this in 5 different languages. And these are like just very like big, large pieces of code. As software becomes more complex, the attack surface increases, and that means that the bad guys have, like a bigger canvas to find for vulnerabilities in these systems. And these are kind of like the largest breach hacks, which happen to be as well the largest hacks in whole crypto. So breaches are not just like as a category like the most hacked in terms of like money lost, but also like per single event. And as we discussed before, some of these hacks are performed as well by national state supported groups. So the stakes are very high. When you do security, something that we always like to do is very important, is to think in terms of economics, because incentives matter, right? Like at the end of the day, the bad guys are rational actors, and they are just trying to maximize the money they make when they, like perform bad things like this. And for this, it's kind of like the second question without ChatGPT, without Google. What do you think is the average bank robbery? Not crypto, leave crypto for a while, leave the metaverse, just like bank robbery in a bank branch in the US by average in 2022? How much do you think like a robbery with a gun standing point, like in a bank branch, could rob? I give you as well like 15 seconds for this. Okay, so Dan goes with $500. Civic goes with 20 million. Have like a big delta here. Samuel doesn't see much news. What do you think? Like, just as a best effort, like, so, like the answer in 2022, like Dan says 2 million. The answer in 2022 was $7,500. You know, like I like the bank industry has, you know, done a lot to improve this and improve their protocols, improve their mechanisms. And right now, yeah, the reality is that this is not a lot of money, or especially if you compare it with the situation that we are. So coming back to the incentives, right? Like the running bridge, which was around 624 million, is 80,000 times more than your average bank robbery. So this is just like a totally different order of magnitude. If you're a criminal or you know, like a criminal organization, you would need to do a bank robbery in a bank branch every day for 220 years to get the same money that you would do one day exploiting the running bridge. So the thing is that like these type of numbers just attract like the most skilled players and the most organized criminals, because like the stakes are so high and the rewards are super high comparing with the traditional systems, right? And here we have kind of like the biggest cases. In yellow we have exploits that were due to poor designs, so like centralized multi-sigs, where there would be like a case of compromised keys, and this is like a more like a Web 2 vulnerability. And then in green we have protocols that their design were robust, or at least their design properties were not compromised, but there was like a software bug in their system. And we can see like there'd be multiple bridges, you know, between the $500 million and $100 million, which again, like these are very large numbers. So the question for us is, you know, how can we do better? Like we have here a situation where we live in a multi-chain world, crypto's multi-chain, so we need bridges. But at the same time, you know, bridging has proven to be, you know, pretty dangerous for some of the users, right, and some of the protocols. So this leads us to like what we introduced before, which are trust minimized bridges. And IBC is one example of those, and the first example of those. So IBC is the first trust minimized bridging standard. There is a lot of jargon in this title, so let's try to unpack it. IBC stands for Inter-Blockchain Communication Protocol. So I guess like here the key idea is that we need to think about it as we think about other internet protocols like TCP and IP. So this is a protocol that is designed to connect and communicate between different blockchains. Doesn't matter if it's like a Cosmos network or a Ethereum network. The idea is to create a standard that any blockchain can use. The second keyword is trust minimized. Trust minimized is the property that you don't need to trust any third party beyond the bridge implementation, so beyond the software, and the source and the target chain. And then the third key point is that this is not just a bridge. This is a standard. This is not a company. It's just a public good, which there are many different implementations and many teams contributing to it. In terms of like to understand a bit IBC a bit better, it's great to think about it like the OSI networking model. So we have different layers to it. Underneath, we have what we call the transport layer. So this is more similar to the TCP IP layer, and you have light clients, relayers, connections, and channels happening. And then you have on top the application layer, like HTTP. And you can have many different types of IBC applications built on top of the transport layer. One kind of like the first application is always like fungible token transfers, but you can have another application that is NFT transfers, interchain queries, so ability for one blockchain to query another blockchain without the need of oracles, and so on. And how this really works, right? So the key insight to understand trust minimized bridges is understand the importance here of light clients. So light clients enable IBC and other trust minimized bridges to exchange messages without trusting other third party. So basically how this works is that blockchain A would have a light client of blockchain B. So then blockchain A doesn't need to trust the relayers and can verify the headers and can verify the information that is getting from the relayers without needing to trust it. Okay, so this gives us a very interesting property, and is that relayers are permissionless. If you're a relayer, even if you are a malicious individual, you are not going to be able to fool with any relevant messages like what we mentioned before, Alice log ETH, Alice burn ETH. You are not going to be able to fool any of the source or target chains, because like they can verify if like a block transition or transactions are actually included in the other blockchain. And this is very important. And of course, why is better, right? Like it's very important that we are here in crypto to remove the middleman, right? And trust minimized bridges enable you to do so, right? Like you can inherit the security properties of both the source and the target chain, and you don't need to trust multi-sigs. You don't need to trust standard validators or validators from a different blockchain. And then another very important piece is that this is, as we mentioned before, this is a full specification. This is a standard, and there are many different teams implementing different implementations and clients for it. And IBC is a standard in the sense that the standards are always hard to bootstrap. But the good news is that IBC is really crossing the chasm. It's been live since October 2021. In the first 18 months of existence, had about 60 billion in total volumes. And as we mentioned before, it started in the Cosmos ecosystem, and now it's growing to other types of blockchains and other ecosystems. So we have teams like Composable Finance implemented with Polkadot, and then other teams integrating IBC with Ethereum, even enterprise blockchains, and so on. And since IBC launched it, like there's no been any hacks to it, but the reality is that there have been a couple of FRIGHTS and a couple of quite scary moments. Even the best designs, doesn't matter how well you design software, like there is always, it doesn't matter how you design like a protocol, there's always like the possibility for a software bug. And as we mentioned, IBC has never been exploited, but there's been a couple of moments that was kind of close to do so. The first one, and most important, is the BNB bridge hack, which we mentioned in the other slide. I think it was around 300 million exploited, and this was BNB bridge hack, which is based actually in Cosmos and Tendermint, even if that is not that publicly announced, but like they were using like a deprecated library, so a null library from Cosmos and IBC. When this happened, a group of researchers kind of went on a deep dive trying to find for related vulnerabilities to this just after the BNB bridge hack, and they did find an important one. It was, it was really like a heroic story, because they were able to patch it, and there was at any point like any asset at risks, but it was close, right? So here's like another question that you may ask, right? Like if even the trust minimized bridges and the best bridge designs are vulnerable to potential massive losses, because that one would have been a massive loss and probably would be in the chart that we saw before, what can we do, right? There are some ideas, right? Some ideas that can improve the situation. First one is having better monitoring and threat detection and prevention systems. And this we can learn a lot from other mission critical industries, right? We can learn from the aviation industry. We can learn from nuclear power and nuclear centrals, right? Then we have as well mitigative measures. So measures that might not protect you against the hack, but really minimize the impact of a hack. That means instead of being stolen $100 million, maybe you get still like 1 million or 500K, right? And we get closer and closer to the model of bank robberies, where every event is not existential either for users or for the bank itself. And then we have as well sort of like multi-bridge aggregators that kind of spread the risk between different like bridges at once. And that's really the kind of problems that we are working on at Range. So we are integrating off-chain monitoring systems and off-chain threat detection systems with on-chain mitigation techniques, creating like a vertical security stacks for blockchains and rollups, and really focusing on building security mechanisms around IDC. And yeah, like some of these on-chain mechanisms that if we have time, we can focus a bit more are rate limits and circuit breakers. So, you know, like a circuit breaker is just the ability to stop certain functionality of a blockchain or stop certain functionality of a bridge or for a certain set of addresses. So you minimize or even prevent a hack. And the rate limits basically look at you know, anomalies in terms of like the values and volumes that go through bridges and these systems. For example, if your bridge has like a daily volume of 10 ETH, right? And this has been the case for the last 6 months. If we detect that next Monday there is an intentional volume of 10,000 ETH, then that might be pretty weird, and we might likely be in a hack situation. So then, like what rate limits do is just accommodate into what the normal use case of a bridge, and really try to accommodate this to protect like the massive hack events that we've seen like in the previous slides. So this is Range. Range is already live in private beta. It's catered to developers. And is live in Osmosis Testnet, and Cosmos Hub as well. And you can, as a developer, like set up alerts, real-time analytics, and security monitoring rules as well. We are also developing like a Range SDK, so you can have like much more flexibility to create like your security monitoring alerts and, you know, like monitoring for certain events, both at the blockchain level but also at the bridge level. That will help us, you know, like be much more effective at both detecting and preventing the next bridge hack. So yeah, like this is coming to the end of my talk. I think right now we have some time for Q&A. This is our website, and yeah, I am AES Monty in Twitter. My DM's open. I always, you know, like down to jam about like security, smart contracts, bridges, and everything in between. So yeah, like feel free to reach me through that as well. Thank you.
Awesome, amazing, Andres. That was really interesting. Can't quite believe just how big the problem is, and you're clearly solving something, you know, very powerful at Scanworks and with your product range. So yeah, big thanks for that. This education is pretty much vital for anyone in Web3. Were there any questions at all from the audience for Andres at this point, or we can wrap up?
yeah, but we can wait, like if there's any questions from the audience, and if not, like we can just call it here.
For sure.
And if you have questions after the talk, as I said, feel free to reach out on Twitter. Yeah, always down to keep the conversation there.
Ten more seconds.
Yeah.
No question, but from Big Mo, it was a lovely conversation. I appreciate it, Big Mo. I agree. Yeah, great chat, Andres. Thanks so much for coming on. That was really clear and insightful. So hopefully get on again if you're down for it later this year. Keen to hear how everything goes with Scanworks. Yeah, best of luck to you and the team and growing, especially up to the next bull run. You're gonna have your work cut out.
Yeah, I mean, like I guess that for us, like we don't really care about bull runs or not, because at the end of the day, like even if it's like a bear market, there is still a lot of value and a lot of value lock in these systems. And yeah, I guess like sort of a security professionals, like the bad guys never sleep, right? So we need to keep at it. But yeah, thank you guys for the time, and thank you for having me. And yeah, looking forward to do it again at some point. So thank you, Calyptus. It's been great to be here.
All right, and cheers, guys, for attending. Hope you see you on the next one.
Take care, guys. Bye bye.
Best. Cheers.